Hi, my name is Abhijeet Malviya and this is my CS622 final project. The project is titled Time Series Forecasting of Stock Prices Using Classical and Deep Learning Models. The goal here was to build a complete machine learning pipeline to predict the next day returns for my ticker NVDA, which is NVIDIA, where I used 10 years of historical data and compared three models: linear regression, random forest, and LSTM, which is long short-term memory. So the task I'm solving is predicting NVIDIA's next day return, which is a percentage change in closing price using only past price and volume data. This is formulated as a supervised regression problem where past patterns are used to estimate future movement. What makes this problem genuinely hard is that stock returns are non-stationary. They don't follow stable patterns over time. Random events like earnings surprises or macro news dominate short-term moves. This connects to the efficient market hypothesis, which says that all available information is already priced in. So a negative R-squared in our results is not a bug, but it's actually the expected outcome, and I'll come back to that later. So for the dataset, I use the yFinance Python library to pull NVIDIA's daily OHLCV data, which is the open, high, low, close, and volume data from January 2015 through December 2024. That gives us 2,515 trading days, which is about 10 years of data. The target variable is next day return, calculated as a percentage change in closing price shifted one day forward. For the training and testing splits, I use an 80-20 chronological split, meaning the model trains on 2015 through 2022 and tests on 2023 through 2024. Crucially, I did not shuffle the data, because that would introduce data leakage in a time series context. So for the methodology pipeline, here's the full pipeline I built. Step 1, I loaded the data using yFinance. And my second step was exploratory data analysis, where I visualized closing prices, trading volume, 30 and 90-day moving averages, daily return distributions, and a correlation heat map. For the third step, I used featured engineering, which I'll cover in the detail next. For the fourth step was the chronological training and testing split. Step 5 was training all three models, and the last step was evaluating them on 4 metrics. So the full stack was Python, yFinance, Pandas, NumPy, scikit-learning for the classical models, and those were the libraries I used, and TensorFlow and Keras for the LSTM, and Matplotlib for the visualizations. So here's feature engineering. Feature engineering was one of the most important and tricky parts of this project. My first attempt used raw closing prices as lag features, and the model reported as R-squared of 1.0. That sounds great, but it's actually a red flag called data leakage. The model was essentially just copying yesterday's price as today's prediction, which is trivially easy and completely useless. So in order to fix this was to switch it to returns, which are the percentage changes as both the features and the target. Returns are stationary and reflect actual market signal rather than just price level. The final feature set has 8 inputs, 5 lagged daily returns, which are T-1 through T-5, and 3 lagged volume percentage changes. The target is the next day return. After dropping null rows from the shifting operations, we end up with 2,508 usable samples, where 2006 are used for training and 502 are used for testing. So I compared 3 models that span the full machine learning spectrum. The first model is the linear regression, which was the baseline. It learns a linear combination of the 8 lag features. It's simple, fast, and tells us what a naive model can achieve. The second model is random forest, an ensemble of 200 decision trees with max depth of 10. The idea is that it should capture nonlinear relationships in the lag features that linear regression misses. It also gives us feature importances. The third and final model is the long short-term memory network, which is short for LSTM. long for LSTM. This is a type of recurrent neural network specifically designed for sequential data. It has two LSTM layers with 64 and 32 units, dropout for regularization, and a final dense output layer. The output data was scaled with min-max scaler and reshaped into the 3D format LSTM expects. It was trained for 50 epochs. So my evaluation metrics measures where I evaluated all models using 4 metrics. MSE, which is the mean squared error, penalizes large errors heavily because of the squaring. RMSE, which is the root mean squared error, brings it back to the same unit as the target return, making it the most interpretable. MAE, which is the mean absolute error, is the average absolute error and more robust to outliers. And finally, R squared. This measures how much variance the model explains compared to simply predicting the mean every time. A value of 1.0 means perfect prediction. 0 means the model is no better than the mean, and negative means it's actually worse. So that was a key metric here. So as for my final results, here are the results. All 3 models achieved an MSE of 0.0010. Linear regression had an RMSE of 0.0321 and R squared of negative 0.0228. Random forest had an RMSE of 0.0322 and R squared of negative 0.0266, which was actually slightly worse than linear regression. And finally, LSTM had the better results, actually the best results. RMSE of 0.0319, MAE of 0.0229, and R squared of negative 0.0107, which is closest to 0. The key insight is that all 3 models perform nearly identical, which is not a failure, it's a meaningful finding. It confirms that short-term stock return prediction from price history alone is extremely difficult, which is consistent with what efficient market hypothesis predicts, which I mentioned it earlier. So for my performance comparison, the bar charts visualize the comparison. On the left, you can see RMSE, which is the LSTM, is marginally lower than the other 2. On the right is R squared, which is LSTM's bar, which is the smallest, meaning it's closest to 0 and therefore the best performing model. The margins are slim but consistent across all 4 metrics, which is why LSTM wins. So let me summarize the 4 key findings. First, LSTM is the best overall model with the lowest error across every metric. Second, random forest showed no ensemble gain over linear regression. This tells us the signal in lag features is simply too weak and noisy to exploit nonlinearity. Third, all 3 models being nearly identical confirms that price history alone is insufficient to reliably predict returns. More powerful features like sentiment data, options flow, or macro indicators would likely be needed. And fourth and final, the data leakage lesson was one of the most important practical takeaways from this project. Getting R squared of 1.0 initially looked like a win, but it was completely wrong. Switching to returns exposed the true difficulty of the problem. So to wrap this up, this project built a full end-to-end machine learning pipeline for stock return forecasting. We collected real market data, did exploratory analysis, engineered proper time series features, and compared 3 models across 4 metrics. LSTM is the winner, but the broader conclusion is that predicting next day stock returns from price history alone is nearly impossible, and that's actually an insightful result. For future work, I would want to add sentiment features from news and social media, explore transformer-based models with attention mechanisms, and reframe the problem as directional classification, predicting up or down, rather than just exact return magnitude. So that's it. Thank you for watching, and I would be happy to answer any questions. Thank you.